So you see everything.
So you want to stand here? The microphone is here.
Yeah.
I'm going to use the mouse to.
Yeah, that's the idea. So.
The online people, you're going to put them on mute, right?
We'd like to have a. Can we use? Pointer? Yeah. But if you do that,
they will say.
oh, they okay. So,
So,
okay, so if I spot here, they will say
We're high tech.
knowledge and press.
Okay. That means. You want to sit? So,
Yeah, so take a nap.
take a nap. Good afternoon, everybody. Can you hear me okay? Okay. It's a great pleasure to welcome you to the 5th KIOS graduate training school on intelligent systems and networks. We have a very exciting program in the next, so starting from today until Friday noon. So we have a very exciting program with 3 distinguished lecturers talking about topics in machine learning, optimization, and control theory. So we are very excited about that. I would like to welcome you to this, and both for the people that are here physically, as well as the online people. I don't know how many we have, but we have several people that are online. We had almost 200 people registered for the course, so it's very exciting. And let me start by, since we're a few minutes late, let me just say that the KIOS Research and Innovation Center of Excellence is very excited about this training school, because it gives an idea, it gives the opportunity to the researchers to get into new topics, and we've been doing this for the last 5 years. And let me just say a few words about our first speaker for today, Professor Cesare Alippi. He's a professor with the Politecnico di Milano in Italy, as well as the Università della Svizzera Italiana di Lugano in Switzerland. He's a visiting professor at the Guangdong University of Technology in Guangzhou, China. He has also been a visiting researcher at UCL, MIT, ESPCI in France, CASIA in China, and A-STAR in Singapore. Professor Alippi is an IEEE Fellow, an Ellis Fellow, and an AAIA Fellow. He's in the Board of Governors of the INNS, the International Neural Network Society. He's a past president of education and an ADCOM member of the IEEE Computational Intelligence Society, and past associate editor of the Transactions on Emerging Topics in Computational Intelligence the IEEE Computational Intelligence magazine, and also the transactions on instrumentation and measurements, as well as the transactions on neural networks. He has received several awards, including the 2018 IEEE CIS Outstanding Computational Intelligence Magazine Paper Award, the 2016 Gabor Award from the International Neural Network Society, and the 2013 IEEE CIS Outstanding Transactions on Neural Networks and Learning Systems Paper Award, as well as several other awards. I'm not going to say everything, sorry. His current research activity addresses adaptation and learning in non-stationary environments, graph learning and intelligence for embedded IoT and cyber-physical systems. He holds 8 patents. He has published 1 monograph, which was also translated in Chinese, 7 edited books, and more than 250 papers in international journals and conference proceedings. So it's a great pleasure to have Cesare with us today. He's a very good friend, excellent friend, and an excellent traveling companion. We have been together in many places, including Tibet and Cambodia, Peru, did I forget many others? So it's great to have him here. And also I should say that the topic that he will cover today is a very hot topic. I know a lot of people at the KIOS are very interested in this, especially with regards to several different applications. So we're really looking forward to it. Thanks.
Thank you, Mario. So thank you, everybody. It's a pleasure to be here after so many years. So I'm missing Cyprus. Yeah, my CV was long, and what is very bad about having a long CV is that you are no more young. Okay, so when your CV will become longer and longer, be worried, be concerned. As Mario says, Professor Policarpo was saying, today we are going to talk about the neural graph processing, which indeed it is a very hot topic. Let's see if I'm also able to move to the next slide. Let's see, in some way, page down. Yeah, page down is working. Yeah. So in this long seminar, I'm going to address 3 major subtopics. At first, I will try, hopefully without playing too much with this stuff, I will enter into 3 major topics. I will say at first, I will give an overview of what I'm going to talk about to try to justify why we do need to process graphs. Why do we need to do that? That is the first question we need to address. And how are we going to do that? I will somehow assume that you are familiar with some basics in machine learning. So that you will see, okay, well, I'm able to use artificial intelligence, machine learning. Why do we need to process graphs in a different way? Then finally, we will enter into the very technical aspects, more technical in a way, which is related to the operators. So we will design architectures, neural architectures, and then we need to define the right operators. Why do we need those operators? Because we want to do something which is useful and having a high expressive computational power. Finally, we will enter into the space and time domain, which means that we will have graphs moving according to dynamics. So everything will change over time, and the graphs, both in topology and attributes, will change over time. And indeed, we want to solve some tasks. For me, I'm interested in forecasting, but you might think of control. Okay? So that is what we are going to see. Let's start with the first topic. And that first, tell me, Stanis.
Sorry to interrupt you. I just want to mention that the slides are online on the homepage of the training school, so you can download them in case you want to take notes.
Or if you want to take a nap. Yes, is that what I want to say? Yeah. Okay, thank you, Stevens. So at first, the Y graphs. Well, if we look at this picture, we know that in many applications, graphs come naturally. So if you have a chemical compound, like in this molecular, you have atoms, you have the bonds, the bindings, the graph is there. Okay, fine. If we look at our neurons, we see that there is a structure in there, and it is resembling that to the graph. If you talk about trees are a very particular special case of graph, so I don't even comment any further on this. In some other cases, graphs are explicit in the sense that when we look at the application, the graph is not coming naturally, but when we pay attention, the graph is in there. It is latent. It is somehow hidden. One example is in the social networks. I don't know, WhatsApp, where you build communities. You have people like in these guys in this inner circle, where you have strong ties. You exchange information. You send images, text, messages, audios. Well, I mean, if I look at this inner circle, each entity in there is a node of the graph. And anytime you communicate with someone, I want to communicate with the Professor Policarpo, I send him a message, we build a connection. So there is a dependency, we are friends. And if you do that frequently over time, you have a very strong connection. So the graph is there. And then maybe that Professor Policarpo and Professor Paianotto, they are friends. So they are communicating each other, maybe with different messages, with a different sharing of information. So there is a connection, a dependency between those two. So we built a graph, a structure where we have entities and we have dependencies. Dependency can be structural, like in a chemical compound, or they can be functional. So we are friends. There is a dependency, a causality between you and me, and things like that, okay? So if we look at a social network, we can design a hierarchy of graphs. So we have a people where we share information more frequently. We have strong ties, inner circle. And then we have a people or communities where we share information with them in a less frequent way, so weak ties. So we are part in a social network of several graphs. And we provide information, we receive information, we want to do inference on what we are doing. Okay, you see the graph is there. Then we will come to the sensor networks. Every time you have a set of sensors, you always can be a graph. Okay, but this is something we will see later on. In reality, I can anticipate a bit without going into any further detail, but let's imagine that we have a smart city where you measure the power consumption at your home. You have all the sensors, let's say one sensor. If it is more than a sensor, you have a vector of sensors, a vector, a matrix, whatever, okay? So each point is an acquisition point, and that is a node of the graph. So if we look at this is the physical structure of the city, this is a real city with all the measurements in there, and then we can abstract by saying that each point is associated with a node of the structure, and then what we have to do is to build the dependencies. So here we might have physical dependencies, which means that this building is electrically connected to, I don't know, another department of this university, you see? But I'm not interested in the physical connections. I'm mostly interested in functional dependencies. So I'm related to you. Then if we are physically connected, that might be even stronger, but not necessary. So what I'm interested in is that if we are physically or there is a functional dependency between any pair of us, it means that we have a bound, we have a constraint. We are not free to do whatever we wish. Every time you introduce a bound, a constraint, you reduce the degrees of freedom. And by reducing the degrees of freedom, that is something that we will use to explore the inference. I will re-elaborate on this. But if this is a smart city and we look at the node attributes, we might have the power consumption within your home, the temperature, or the temperatures of the different rooms, the date and time. If it is a weekday, if we are rich, the number of people in the family, many sensors. They can be physical or they can be virtual. They can even be categorical information. Are you happy? Yes or no. Do you like it? Yes, no. Okay. If we have now a couple of nodes and we look at the edges, we can assign attributes to the edges. If we have signals, two signals, so this is the power consumption of a node, this is a power consumption of another home, and we have signals, we have many ways to build dependencies. The Pearson correlation, look for correlation, the Granger causality. But we might only say that that point is physically connected to the other point. So without any further elaborating, we might have the weather correlation. So if my home is in the shadow because there is the Kiko Mountain, and your home is again in the shadow because of the same mountain, maybe in a different place, you will share some dependency, you see? And the cable length. So if we are physically connected, we know that between you and me, there is a cable whose length is 1 kilometer. So these are examples of attributes. So at the end of the day, what you have a graph, and what you want to do is to process the graph. If you build a graph by looking at what is going on in one day, you generate the graph 1. If you look at what is happening tomorrow, 24 hours, you have a second graph. And then what you can do is to generate a graph stream. It's like the extension of a time series, if you wish, where at each sample, what you have is not a vector of information or a scalar information or a multivariate information, but you have a more complex structure whose topology can change with time as with attributes as information. Is that clear? So very, very simple. Some examples. In reality, every time you have a sensors, you can build a graph, as I said. So if we look at the social networks, graphs are there. Traffic prediction, these are just examples. If you have a traffic, you have the different elements, different sensors, roads are related because they are topologically connected. But then there is also the functional dependency. If one road is entering into the other one, clearly traffic jam is related, you see? So you have edges. In physics, I mean, if you look at the CERN with all these particles, trajectories, those are links. In recommending systems, reinforcement learning, so all the applications you can think of. But now you might ask me, but do we really need to represent something as a graph? And do we really need to process graphs in a different way? We are very good in processing vectors, matrices, sensors, tensors. So if we are able to deal with tensors and we have a huge data stream, if we have deep learning, so why do we need to do something different? So in other terms, if I look at this graph, which is a very simple graph, associated with each node, let's imagine that you have a signal, okay? So you have a signal. You decide which sensor. You want temperature sensor, 1, 2, 3, 4, 5, there are 5 in this room. Do we agree that they are correct, connected somehow functionally? I might decide, okay, I take that data sensor there, I look at the signal, look at this temperature sensor here, I take the signal, I do a linear correlation, I build an edge. They are dependent. And if I do that, I generate this graph. And clearly, I can take a picture or generate a graph today. I can do that tomorrow and so on. So I can generate a graph stream. And then I can process that graph stream. But do I really need to do that or not? This is the key point. You know, the other possibility is to say, yes, but listen, we are starting from the signals. The signals are there. So I put one signal, another signal, you know, I built a matrix, which is exactly what I have here. It is this X matrix. All the information is in the measurements. So why do I need to build something which is complex with all these dependencies? If my inductive inference engine is powerful enough, and we know that deep learning for neural networks, they are able to solve and implement any measurable function. So it means that let me ask the neural network to extract all the information in there, and they will be able to solve my task without the need to build a graph. Did you get the point? So all the information is, again, here. So why am I so interested in doing something complex, which means also time-consuming, in building a structure which is also containing something extra, which are the edges and so on? And then we need to design architectures that need to look at the topology, which is changing with time. So only complexity. Do we really need to do that? Apparently not. So that apparently in reality means that in principle, it appears that it is not convenient to do this operation. So if we have the signals, we process the signals as we do. We have been doing that for me, almost 35 years. So why should I move into graphs? In other cases, it is not true, which means that if you have a physical compound, some chemical molecule like this one, the graph is in there. And if you only consider the atoms, which is the signal, you are missing some relevant part. So in some cases, it is not true. In some cases, it is in principle true that I should not move to graphs. And now we are entering into something which seems philosophical, but it is not philosophical at all. So we were starting in machine learning with hand-engineered features. So we were extracting features, and then classifier, regression, whatever, you know, building an artificial inductive system. And then we said, but listen, why do we need to do this exercise to handcraft the features when we can use deep learning architectures, which they will be able also to extract the features. They will do feature extraction for us. And that is what the deep learning is doing, end-to-end learning. You learn end-to-end. That is correct, but if we look at reality, we see that having a lot of data is good, is enough. All the information is in there. If we have all the signals, the information is in there, but our inference engines are not effective enough in being able to extract that information. In other terms, if we know if we have the prior, which is telling us that there is a dependency between the two of us, and we ignore that prior, then we lose the expressive power. We don't exploit the prior we have. And the inference engine will be much less effective, even though in principle, all the information is in the data. Okay, that is the key point. This is called inductive bias. So every time you have a prior, you want to use the prior. If you know that a system model is linear, why should you use nonlinear systems? You see, that is the point. So an inductive bias is any type of prior that you have. And when you integrate that prior directly into the architecture, then you can get a significant advantage in performance. It can be really significant. Then, as I said, in principle, you have infinity data, and you expect the inference engine to be able to find a smart solution. But that smart solution is not as smart as the one that is already integrating the constraints that you have. And they are coming from the priors you have or you can learn. Okay? That is the point. So if we have applications, how can I represent a graph? This is an example or a set of examples. So if we have a molecules, then we can build this graph. Do you agree with me? To hydrogenum, the same graph, the same node, the same color means the same attributes. And oxygen is a different node. We have 3 nodes that are connected in that way. If you have a master spring system, what do we do? In a finite elements, we decompose the spring in finite elements. You generate a composition, submodules, and you transform every single submodule in a node of the graph. And then you have the mass, which is this blue element, which is interconnected with every single component. And then you process the graph. Or if you have an n-body system, the solar system, this would be a very nice example. We want to learn the laws of gravity by just looking at the trajectory. We have the planets, we have the solar, the sun in the middle, or we believe it is in the middle. We look at the measurements and you build your system by starting from this graph. So everything is connected with that. Rigid body system. So you have these boards, okay? I'm sure that you are good with that. So you go and play. So what you have, the trajectory, the dynamics of those boards on the table. And you have the table, which is the element, one of the elements of this game. Parser trees, so you want to do parsing. You generate a tree is a graph. If you have a picture, so if I look at this table, I see that I have different elements. Each element is a node of the graph. So I have a bottle, a laptop, a mouse, sunglasses, a mic, and so on. Which are the dependencies? The bottle is on the table. The mouse is on the table and it is close to the bottle. You see, there is a dependency and they are interdependent. So graphs, let's try to understand what they are. So we have different types of graphs. They can be directed. Directed, you have, for instance, causality. In a causal system, you have that something is inducing something else. So there is a one direction. Causality is defining the direction. In some cases, they are undirected. So the table and the bottle, they are connected. So the bottle is on the table, and the table is keeping up the bottle, also bidirectional. So which means that we are not interested in the direction. There is not a flow of information. The flow is bidirectional. Multigraph entities can be connected through many many dimensions. We can have attributes which are properties. They can be any type. They can be at the node level, which means that we have, I don't know, vector, tensors, graphs, images, videos associated with a node. We can have the same attributes associated with edges, the arcs. Or we might have also global attributes. So I'm looking at the graph, and the property I'm interested in is at the graph level, at the entire graph level. So, for instance, I look at the chemical compound, and the property is that whether that compound is going to explode one day, is stable or is not stable. That is a property of the compound. It is at the graph level. Yeah, so this is, in some cases, so if we have graphs and we want to process graphs, we have tasks. And the task can be at the node level. At the node level, I have many people here. We know what we are going, let's say, to vote based on my features, on my nodes. So I behave in some way, I have a vector of features, and I'm interested to know what Professor Policarpo will vote in next polls. So he's a node of this graph, and they want to infer something at his level. Or we are photovoltaic cells, each of us, we are producing energy, well, we acquire power, and I want to forecast for each of us, each node, which will be the next day values, how much energy I will produce tomorrow in 24 hours, or at a given instant of time, how much power I will get. That is something at the node levels. Or we might be interested in tasks where edges are involved. If we are friends and we are connected, if you believe A, you believe B, you believe A, you believe B. Am I with a Professor Panayiotou connected or not? So are we friends or not? We don't have the direct link, but I want to forecast whether we are connected and the intensity and all the features associated with the connection. That is a task which is at the edge level. At the graph level, entire graph level, for instance, I might be interested, if you are photovoltaic cells, to know which is the total net power you will give me tomorrow in Cyprus at 10 a.m. Okay? Something which is global. Okay, so how do we represent the graph? Fast is very easy. So we know that if this is a graph, there are basically today the three major entities we need to define. The first one is the topology of the graph. This goes through the adjacency matrix, which is a binary entity. So basically, I'm saying whether it is n by n if we have n nodes. So n by n. I'm saying node 1 is connected with node 1. Do we have a subgroup? No. Node 1 is connected with node 3 and with node 4. One node 3 and node 4. So basically, the adjacency matrix has binary values in there, and it is telling us if we are connected in terms of topology. So that is one issue. Then we needed to characterize and represent information. Information can be associated with the nodes. So all the vectors, matrices, images you have per each node can be a tensor. So this one, node 1 you have, in this case, is the 3.1, 0.2, you have the first line. And then you have information associated with node 2, 3, 4, 5. So you have a matrix. And then you have the information associated with the edges. So I'm saying that between 1 and the 3, node 1 and node 3, between node 1 and node 3, the information is 0.8. If you have a vector, you build a tensor. If you have something more complex, you build a graph or a registry. So through the adjacency matrix, you model topology, and then you have the information which is associated with the nodes and the edges. So adjacency X and E, they are matrices, they are tensors. So we can use TensorFlow to process that. So we can use any machine learning. Another way, when the edges are associated with a scalar value, is to have the adjacency matrix coinciding with the edge matrix, which means that associated with this matrix, the topology converges on the content of information associated with the edges. But either way is fine. So we have matrices, we have tensors, and so we can design processing blocks. If we have matrices, we can write, then we can say they are images, and we can do any processing. So again, this is a very high level, and then in the second part of the lecture, I will focus deep on the operators. But to understand where we are, so okay, we have matrices, we have images, if you wish. Okay, so we have images. What do we do in terms of operators? Well, if we have images, we can use a convolutional network, convolutional neural networks, isn't it? And when we look at those architectures, we always should think of what they are doing, which are the properties that they are exploring. So we know that we should use convolution. So convolution, neural networks where what we have as input brings inside the concept of physical proximity. So if we have a dependency in space, this pixel is highly in probability correlated with my close friend in the neighborhood, because that is an image, then we should use a convolutional neural network. So you see, every time we do propose an architecture, we do that because we have some prior. So dependency in space, we do convolution. Dependency in time, we do temporal convolution. Dependency in space and time, we do space and time convolution. If we look at this architecture that everybody knows, we see that there are operators. But if we know that there is this physical locality principle, and we want to exploit that, we use convolutions, and we do battery of convolutions. So a bank of filters, which is what we have here. Then we call the outcome feature maps. And then we do subsampling. We shrink the information. And then it is deep architecture, convolution, subsampling, which is called also pooling. So in a CNN, what we do is convolution, pooling, convolution, pooling, convolution, pooling. And then at the end, we have some fully connected architectures, which is taking the outcome of these tiny images, which are summing up what we have, and we solve our task. In this case, it will be a classification of the image content. Okay? So, okay. So we know the convolution operator, you take a window, you need to design a kernel. We know that the kernels will need to be learned, so we will have a bank of filters, but each filter is going to be learned. And then when we look at this kernel, this kernel is moving all over the image, which means that conceptually, it is like having a layer of a neural network where all the receptive fields keep the same kernel. They are identical neurons with always the same kernel. And that is why we do this shift, maybe with a stride. Yeah, I said we can have many filters, many kernels in parallel, and that is fine. We know that we need to shrink from one layer to the next one, and then we have a pooling, subsetting. There are many operators. One might be max pooling. You take a window, this 2x2 window, you take the maximum value coming from the convolution, so the affinity between the kernel and the subimage which was in there, and you take the maximum value. You want to exploit the maximum affinity. Or you can do the average pooling. Anyway, these are hyperparameters. You select them, okay? But you shrink the information because at the end of the day, you want to make a decision. Classification, regression, control, prediction, whatever. So this is something that we are familiar with. And now if we have a graphs, what are we supposed to do? Conceptually, I would like very much to be able to design a graph neural network, like a convolutional neural network. If I, Thomas, Christos, and Marius are friends, we are very much related. We share some dependency. Wow, that is the locality principle. It is not maybe physical, but if there is a dependency, a functional dependency between the four of us. So we can do convolution. You say the appropriate operator. You don't do something different. You do convolution because we are friends. We share something together. So low pass filter, because that is what we do with convolution. So how to move from a convolutional neural network to a graph convolutional neural network? Well, something like this. So if this is the neighborhood that we have in the picture, which is this one. So yellow pixel, and around we have our physically related closing space friends. When we look at the graph, if we are in the center, at the one hop, the inner circle, if you wish, this one, we have these pinkish entities, Thomas, Marius, and Christos. We are very much related, maybe with the different intensities. We share information, but we are related. And then if we move in the graph, so I'm focusing on one node, I'm looking around in the diffusion process at this hop number 2, we have these blue entities. They are related with me at a lower level. At the second level, if we wish. We are friends of friends. You see? So the dependency is there, but is not direct. If it is direct and if it is strong, there is already one direct connection between me and them. Otherwise, we need to look around. He is a friend of my friend. You see, let's put it that way. So the dependency is not direct, but if we are, if I'm going to vote pink, he's going to vote pink, and if he's a friend of someone, he might vote pink. You see? That is the link over space, but now space is the in terms of dependencies. Convolution. Well, I mean, we can extend convolution in a very simple way. If I am this node, I need to do the convolution. What do I do? I look at my neighborhood, my neighbors. I have this one, and this one. I have these edges. I have a kernel. I do convolution, and I generate the output of the convolution. I do that for all elements, and what you get is the convoluted part. Then we will formalize the concept. Pooling. Well, pooling, you have a graph. It can be an arch graph. Think of a social network where you have millions of nodes. And then what you want to do is to shrink the topology. If we are connected and we are a click, we can collapse. We can cluster ourselves together in one single meta node. And then you shrink. And so if you remember the architecture, we have convolution, pooling, convolution, pooling, convolution, pooling. And then at the end, we make the final decision. So something very similar. And at the end, what is a graph neural network? Well, it is a convolutional neural network, which is doing convolution in a deep way over a graph. So a bank of filters. Now we are processing the graph structure and then pooling. You say this one is collapsing in the green node, in the blue node, in the orange node. And then again, convolution, and then shrinking. And then finally, I want something which is maybe a multi-layer perceptron structure, maybe deep, able to make a classification of what? Of my input graph, of my input node, of something which is at the graph level. You see? Can we use other architectures? Of course, all the architectures, or most of the architectures that you have seen in machine learning can be extended to graphs. So, while we know that autoencoders are very nice, so one possibility is to use graph autoencoders, which means that you start with a graph, you do graph convolution networks, you do pooling, and then you have a vectors, that is the latent space. And then from the latent space, you have a vector. You don't have any more a graph. You want to go back to a graph. Going back to a graph means that you need to generate the adjacency matrix and the matrices associated with the edges and the nodes, the information. And since this one is a vector, you use a dense multi-layer perceptron. Can be deep. Okay? So this is an autoencoder. Fine. And if you're able to train your autoencoder and you cut at this level, what you are doing an embedding from a graph into a vector. And if you have a vector, you're able to process the vector with a traditional. So for instance, with a support vector machine. Now you have a vector, you need to process graphs, you want to build a classifier with a support vector machine, you do an embedding, and then you apply your favorite method. But in reality, we will see that we want to do more than this. But this is a possibility. You don't like graphs, you don't want to process graphs, you do an autoencoder, which is learning for you the dependency, the mapping, the embedding, and then you use your favorite classical structure of machine learning. But what you get is not as powerful as processing with the proper operators. So something that we might wish to do, but again, is not as powerful as processing in proper way graphs, is to do something like this. You move from a graph into a vectors. And then if you have a graph streams where all the topologies can change with time, they are very strange entities, bad beasts. The easiest way, in a way, would be to embed each graph into vectors. Then you have a stream of vectors and they use traditional machine learning tools. Okay? Neural tool, okay, that is fine. This is not the best way, but if you want to do that, feel free to do that. It's very simple, very easy, very harmless. So if we want to do this exercise, how can we move from a graph to a embedding, to a vector? And then we will see that we don't want to do this anymore, and we will design ad hoc operators. Okay. So at first we should ask ourselves which types of graphs are we interested in. I might say that we are interested in graphs where we have generic attributes. Attributes can be at the node level, at the edge level, at the graph, entire graph level. They can be scalar values, vectors, tensors, images. They can be graphs. They can be videos, can be whatever you wish. That's fine. We want to deal with the framework where at each time sample, if there is time, they change in topology, in order. Look at this. The topology is changing. Why? But because maybe that today I and Thomas didn't exchange any information. So there is no link today, but there it will be tomorrow, you see? So the topology can change in terms of number of nodes and edges. We want to be able to deal with this framework. We might have situations where we have identified vertices. What does it mean? That if one sample is associated with the yellow sensor, we know it is the next sample coming from the yellow sensor. Over time, this node is this node. They have the same name. If it is me today, it will be me tomorrow. We don't want to anonymize. But if we anonymize people, then we have the problem how to say that me today is that entity tomorrow. You see? If they are not identified, like in sensor networks, for instance, you have this framework where the graph changes completely over time, and you are not able to say that this node is that node. There is a connection. You have only a graph that is changing, very complex problem. So the good news is that when we look at these strange entities where attributes can change with time, the topology can change with time too, we can claim that this structure generate a probability space. So there is the concept of a Lebesgue measurable functions in there, and we can induce the concept of probability. This is a very recent result, 2016. Again, we are changing topologies, entities, information. We want to do processing. Do we have the concept of affinity? Do we have a distance? This strange graph and this strange graph, are they similar? How can I measure the distance? And if there is a distance, do they induce some probability? There is a probability space behind or not? The answer is yes, okay? Which is very important. Otherwise, I mean, go out and we enjoy coffee. So indeed, there is what is called a graph distance between two graphs. We can evaluate the distance, and having this set of graphs and the distance, we can induce a probability space. Then, if there is a probability space, we can start thinking of time variance, stationarity, you name all those properties. Distributions, it is a probability space. Then we have distributions. Which type of distribution do we have? Do we have stationarity? Okay, so the concept of stationarity, the concept of affinity, the concept of expected value of covariant matrix exists in the proper space, in the proper way, which is according Fréchet. Okay, so if you're familiar with the Fréchet, you are able to find what is the expected graph, which doesn't mean it is a real graph. It is a concept. And the expected graph, most of the time, is a set of graphs. So you don't have only one entity. You have a number of entities that all together, all this set, is the expected value. So it is a bit more complex. But just to understand, let's imagine that we want to design some enzymes. So we have the enzymes, they can be whatever, but they come from a concept, the concept of enzymes. So if I ask the process generating the data, give me one enzyme. Oh, here it is. It's the first one, yeah. If I ask the process, give me another one, it is a random variable. Give me another one. It is this one. Another one, this one, another one, this one. Are they different? Of course they are. In topology, in attributes, whatever, still they come from an unknown distribution. Okay? That is what is real. If we have a characters, it is something like that. If you handwrite characters and you want to classify them, I mean, this is an A, you know, think of the way that they implement algorithms to try to extract the graph. You know, this is an A, this is an A, this is an A. You see, nodes and edges can change. Still, they belong to the same characters, and so on. So there is the conceptual hidden behind in this probability space and the distribution that needs to be addressed in a proper way. Okay, it's not that you take the expectation as we do every day. No, but there it is in there. And in terms of distances, how can we say that this graph, look at the tip of my fingers, and this graph, only 4, so which is the distance between these two entities? Let's imagine they are identified, so I know that this should be the match. But are they similar? Are they not similar? Which is the value? So we need to define the distance. So in that space, one possibility to define the distance is called the graph edit distance, which in other terms is looking at the cost in moving from one graph to the other one. So which are the operations that we need to do to move this graph into this graph? So first, if this has 5 nodes and this has 4, I need to build a new node. There is a cost. And then we need to match the attributes, which might be different. So the distance between attributes at the edge and node level. So you have the operations in this graph edit distance are related to insertion, deletion of nodes, insertion or deletion, removal of edges. You have a cost that can be expressed as a kernel. And then once you have the same topology, you need to look at the distance in terms of attributes. This one is a 3.2, this one is 2, the difference. Or a distance between this one, you define the distance. So at the node and the edge level, so there is another cost. So at the end, you have an entity, which is this graph edit distance, and the distance between those two graphs comes from the minimization of this term, of this function. Okay, this comes from J, from basic foundational research. You can learn those cost functions, those curves. So there are ways that, if you have enough data, allow you to learn the kernels, evaluating the different distances. So embedding methods, well, when we need to stop for the break, you tell me. So very quick, anyway. So if now we have the concept of graphs, we have a probability, we have the concept of distance, and we want to do the embedding. We don't like graphs. We like vectors. If I have this graph, I want a vector, and then I want to process vectors. How can I do that? So there are different methods. Distance-based methods is similar to representation, multidimensional scaling, or we can use neural approaches. We saw autoencoders. Autoencoders are still there, but we can use also adversarial learning if we want to impose a probability density function to the distribution. So we want to control the distribution in the vector space. But in a very simple way, this similarity representation, the goal is the following. You start from a graph, here's a blue graph, you want to end up with a vector. That is what you want to do, from a graph to a vector. The idea is the following. So you split the data, the graphs you have in two sets. The first one is called the training graph, and the second one is the prototype graphs. The prototypes graphs can be picked up randomly according to the distribution in this data set, or there are techniques which allow you to pick up the most representatives. And what you do now, in order to generate the embedding, you take the new graph and you try to look at the distance between this blue graph and the first prototype. It's like a projection, but it's not a projection. So I have this entity and I say, how this graph is similar to this one? 7.2, that is the first entry of the vector. And then again, this one. How this one is similar to this graph? Minus 0.5, second entry. You see, you use the graph edit distance to evaluate the distances, and you populate a new vector, whose size depends on the number of prototypes. This training graph is used to learn the distance d, which most of times are parameterized functions, and you want to learn what does it mean to evaluate the distance, the costs associated with node insertion, delay removal, attributes, changes, and so on. If you do this operation, you will see that if these operations are very nonlinear and they change completely the manifold that you have. So they are very powerful. They converge in probability in the sense that if you increase the number of prototypes, you can guarantee that you can keep up to some level the semi-definition content, but you map into something which now it is a vector. And if it is a vector, you can process that. In a multidimensional scaling, what you want to do is to do this embedding, this mapping, by keeping the interdistances in the transformed space. So if in the graph space there are some distances, we want that in the embedded vector space, the distances are preserved at hand. We want to, if I'm distant from, I don't know, Stelios 0.5, I would like very much that when we are embedded into vectors, the distance in the vector space is a 0.5. Clearly, we need to find a way to harmonize this, and that is what the multidimensional scaling is doing. So it's similar to the previous method, but now tries to preserve the distances into the transformer space. You can do embeddings in any manifold. If they are controllable manifolds, it is easy to evaluate the distance on a manifold. If it is a sphere or it is a hyperbolic, we know the function that is telling us the distance on the manifold. Differently, if the manifold is not controlled, it is much more difficult to evaluate the geodesy, the distance between those 2 points. We can do that, but it comes at very high computational cost, which most of the times is not justified. So in this operation, when we do the embedding, we try to control the space in the proper way, and we try to use some manifolds which are controllable according to the distances on the manifold. graphs autoencoders. We saw that before. Again, we start from graphs. We have graphs. So if we want to process graphs, we cannot use convolutional neural networks. We need to use a graph convolutional neural networks. And then convolution pooling, at the end, you have vectors, latent space. And from the latent space, you can go back to the graph through a decoder, which is a dense architecture, from the vector space to the graph space. So basically what you want to do, you move from a graph domain, you do the embeddings, you have points in some space where you can nicely evaluate the distances. And the autoencoders are there for this, but when you have the autoencoder like this one, the mapping, you can get the vector, but you cannot guarantee the concept of vicinity, affinity. So if I map this graph into a vector and this graph into another vector, if they are similar, I cannot guarantee they are close in the vector space. So I don't have the concept of affinity, which means that we don't have the concept of probability, and then we need and we want to control or to induce the probability. So if this is a bottle and this one is another bottle, I would like them to be mapped in the latent space so that there it will be a distribution of the bottles in that space. And if they are close here, they need to be close in probability in the embedded space. If you want to induce this, you needed to use adversarial autoencoders. So with the adversarial autoencoders, you have the encoding decoding module, which is this one. You want to impose on the latent space here some distribution, Gaussian, for instance, low uniformity, it depends. And you build an architecture, which is the adversarial architecture, that is not only building the concept of embedding of the graph into a vector, but you force also the distribution on that latent space. If you want it, if you want the points to follow a Gaussian distribution, they will follow Gaussian distribution. Which means that if we are close to each other, we need to be close in that space. If we are far in the regional space, we must be one at least in the tails, in the queues of the distribution. By doing this, we have the statistics, and then we can do all the irregular processes. Otherwise, if you just and simply use a random embeddings like this one, it does not make any sense to use the statistic in order to make a decision. You cannot say, for instance, that this graph is an outlier because you don't have the concept, controllable concept of probability in that space. You need to induce that. Right, so I think that we can have a break now. So to sum up this part of the lecture, I just wanted to hopefully to convince you that it is worth to process graphs, but they are very strange items. They change in topology and they require ad hoc processing. Though, if you do that, you will be surprised by the achievements you get after doing inference, because you are going to exploit the problem. People, what they tend to do, because we don't like graphs, is to take a graph and hide the graph, which means we do embeddings. We move from graphs, which is there, but we don't want to use them. We do embedding into vectors. If you have vectors, then you have a multivariate time series, whatever, you know, and then you use your tools. Pay attention. There are ways to do that in the proper way, but keep in mind that not necessarily you have the concept of probability there as you expect. And if you take some expected value, it's not what you are expecting,
And the one point not necessarily is close to another one unless you control the operation. You can do that through the multi-scaling methods or through adversarial techniques, not just by building embeddings. Okay? Now, this is something which is doable. You can do that. You can use then all the techniques you know from signal processing, whatever, fine. But if you go back to the graph and you design operators in the graph space and architectures in the graph space directly, you will be surprised by the results. And that is what we are going to see here on. Okay, so let's stop here. If you have questions, of course, I'm here. At first, is that clear? Hopefully. Yes. In the second part, I will go back to the operators and we will see step by step how to design the operators. Okay, so convolution and pooling and all these things.
Any questions for this part?
You have a question? No. No.
Yeah. I don't know whether it's something that you said here. So when you speak about graphs, it seems that they are all.
Yeah.
This one?
For the online.
Sorry. So graphs are only undirected, or you can handle directed graphs?
You can handle directly graphs as well, but
How do you?
okay, in order to do that, you needed to use a message passing operators. And that is something that is part of the next lecture, which means that when you do, if you wish, convolution, I need to do convolution only with the elements that are providing the information to me. Okay, so you need to be selective. You don't take, we are connected and so let's do convolution. No. If you are influencing me, I do convolution. If I'm influencing someone else, it will be someone else that will look at that edge. You see, you don't mix up things. That is part of causality, otherwise you lose everything. So there is diffusion in the process. But that is something, in order to do that, that you need to design ad hoc operators. Message passing. Very cool. Then, yeah.
So we take a 30-minute break. We start again at 4 minutes.
Okay.
Okay.
Okay. So let's start at the second part of the presentation. In the first part, as I said, I was telling you that if you don't like graphs, a very easy way is to embed graphs in vectors. But if you do that operation, you should pay attention to what you do and what you get in terms of improvement in accuracy on your task, which can be any task related to machine learning. So classification, prediction, regression, even control. I mean, it is up to you. It depends on how you build on top of that, won't be the same. Okay? Now, what I'm saying is that if you have a graph and we have the opportunity to work on graphs, let's do that. So if we now, and that is the part of what we are going to see now, if I look at a graph, all the edges are introducing constraints. So which means that the nodes are not free to do what they want. Those constraints are reducing the degrees of freedom of your graph system. And that is a real value. It is the inductive bias that we want to exploit in order to do inference. Okay, that is the major message. But in order to do that, we need to design ad hoc operators. And therefore, we will have all, most of the architectures we are familiar with coming from machine learning in the graph space. And the operators will work there. The good news is that there are plenty of libraries. Many of them has been designed by us, and they are freely available. So you don't need to waste time to rebuild the operators. They're there. But you need to understand how to use them and why. That is basically it. So processing operators. Something happened. Basically, in a graph processing, independently from the task you want to solve, you have two families of operators. One derives from the concept of convolution, and you want to extend the concept. So, Thomas, you were asking what I'm going to do if I have a directed graph. Okay, so you need to design the operators that is taking into account of information. And the second one is pooling. You want to shrink the information. And you want to do that because at the end of the day, you want to solve your task. You don't want the proliferation of information. You need to keep the information converging, like in a bottleneck, towards the output. So those are the two major operators. And so towards graph convolutions, in the first part of the presentation, we got a glimpse of the idea. Okay, so we look at our neighbors, we try to get information from them, and then we mix everything together in order to update my state. So let's revisit that in a deeper way. So let's look at a picture. Again, convolutional neural network. We know that in a picture, there is the locality principle. If I am a pixel, it is very high the probability that the pixel next to me will be very highly correlated with me. And then you have this sequential probability, locality principle, which is saying that if I'm the pixel, it is very high the probability that pixels in my neighborhood, not only by me, but in the neighborhood, will be somehow related. Okay, and that is the reason why we use convolutions. We know that convolutions are low-pass filters, and we might not be very happy about this. Okay, but we will see that later. Okay, so if this is a picture, we have the locality principles. I can build a graph out of the picture. So every pixel becomes a node of my graph, and all pixels are connected by edges. Do we have information associated with edges? No, not necessarily. I mean, we don't need always to have information associated with edges. Why? Because sometimes we don't know what we should put there. So it's very frequent the case where we know that we are connected, and that's it. Why? Because we were exchanging one message. It's not relevant, the message that we were exchanging, but the fact that there is a link. So we might just model the link as, yes, there is a connection, no features associated with the edge. Okay, so we don't always need features associated with edges or features associated with nodes. Clearly, we need something. But we don't need to put everything together. Sometimes they can degenerate depending on which type of information you have. So the receptive field of a convolutional neural network reflects the underlying grid structure. And the convolutional neural network exploits the inductive bias, so the prior. And the prior is the fact that we have this locality principle, locality space. We are closing probability. But not everything can be cast in a grid. And in particular, if we look at graphs, they are at first a nice representation of irregular structures. Fine. And we would like very much to try to extend and generalize the concept of convolution. So if I sit myself on this black node, I look at around me, and there are entities which are similar to me because they belong to my node. Maybe I don't know how similar they are because associated with a link, an edge, there is not a value. But if the edge is there, it means that we are related, and that's it. Maybe weak, strong, we don't know that. If we know that, that is an information you put on. Okay? If you know more, you put a vector, you put a subgraph on the edge. You put what you have. Okay, so again, Euclidean spaces. If we have a convolution over this vector, convolution over a signal, convolution over time, we will see tomorrow because we will do convolution over time and space. Okay, but we know how to do that. You build the kernel, whatever the kernel is. If you don't know the kernel, you will learn the kernel. And we know it is a very nice operator, beautiful properties. We can even move through a Fourier transform in some frequency domain. We do that with graphs too. Okay? So if it is appropriate, we do that. We have some extension of the concept of frequencies, which are a bit tricky, but there are many operators that operate in the frequency domain for graphs. If we have a 2D image picture, well, we have this kernel becomes a two-dimensional. We know that the size of the kernel is a hyperparameter of my method. Okay, so that's fine. And then we know how to do convolution. So it's a linear operator, and it does operate on Euclidean spaces. But if we have a graph, this space is not Euclidean at first. And we have major challenges. Why? Because if we look at the graphs over time, which means that we have a process, which is this bottle, that is generating graphs and z's. Maybe that the distribution is stationary in the J space, in that graph space I was telling you before. I say, okay, give me an IID sample, a graph. So the graph is coming out. Give me another one. The graph is coming out. They are different in topology, number of nodes, number of edges, for sure, number of attributes in probability. Still, the process is stationary. If it is a dynamic process, still you have the concept of a time invariant process. And then you will generate these graphs having time in there. So it will be a stochastic process where the random variables are dependent over time at least, but the topology will change. And so there are this type of moves. So the key point of having graphs is that they share a variable number of neighbors. So if you want to tell me I want the 3x3 window over my picture, my image, well, maybe that the number of nodes changes, and then you might lose the concept of orientation. Because in a graph, unless they are identified, so you know that this node is this node, which is this node, which is this node, oops, it is disappearing, or it is coming back, you know, so you know it is coming from a sensor. I have the sensor, I know it is always this node. I don't have the sample, maybe it was a communication fault. But the infrastructure is fine. It's not a faulty infrastructure. I had a communication fault in one sample. That's fine. Who cares? You see? So here's maybe a tiny invariant process. That's fine. But the key point is that if we want to do convolution, we have this type of situations where the number of elements, if I'm the black node, change. Or if I'm the central one, you know, changing the number. So we need to deal with this, which is not too difficult. So let's look at the notation in a formal way now. So a graph is composed by the set of vertices, the nodes, and the set of edges. And the set of nodes are connected by elements in the set of edges. Fine. Then we have information, which is associated with the nodes, and this is the capital X matrix. It is the node attribute. It is called also graph signal. Why? Because if you have a sensor network associated with a node, you have signal. And that's why it is called the graph signal, because if you look at the graph altogether, each node contains a signal or a time series, and then you look at everything together, what you have is the multivariate time series, which is associated with your graph. So the name is graph signal. So basically, it is the information associated with the nodes. You take all these signals, whatever they are, you put them together in this capital X matrix. And by D, capital N is the number of nodes, dx is the dimension of the vector associated with the node. If it is over time, dx is the number of samples. If it is a vector, it is the size, the cardinality of the vector. If you have a space, the vector, and time, you will have a matrix. Okay? But that is too much. Okay. So again, when we look at this node inside, we have a vector which is x4, and it is a vector. Just for simplicity, I will assume that if we have a set of vector sensors, they will associate it with a vector. You define the maximum, the size of the maximum size of the vector, and all the nodes will have that size. It doesn't imply that we will need all the sensors in the node, but we need to dimension the space. So I'm saying that associated with a node, there is a maximum number of information, of entities, of real values, whatever they are, stored inside. Okay? If they are there, fine. If they are not there because you didn't buy the sensor, you put a 0. That's it. As simple as that. Okay? This is only to be able to deal with the computer issues when you do coding. So you need to dimension the data structure in order to keep a new. Then we have the topology. In a graph processing, we like very much to decouple the edge matrix, which is containing the information associated with the edges, from the topology. Why? Because the topology is telling you something. And the information associated with the edges, it is something else. If I'm connected, that is an extra information. Then if related to the connection, there is also an entity, a strength, a vector, that is something different. So we like very much to decouple the two entities. And that goes through the adjacency matrix, which might be weighted. Weighted means normalized. That's it. So you have something like this. If your graph is undirected, these adjacency matrix will be symmetrical, which means that there is not a one direction. If you have a directed graph, the adjacency matrix won't be symmetrical. And that will have effect on the way we will process information within the graph, as Thomas was asking before. So if we have a causality that is in the adjacency matrix. And that is the reason why we want to decouple that from the E matrix, which is contained information associated with edges. Then we introduce another matrix, which is a diagonal matrix, which is called the degree matrix. The degree matrix is basically looking at every single node, and it is storing the number of connections of that node. So if I'm the node 1, I, and I'm connected to Thomas, Christos, and Marius, we have 3 connections. So the degree matrix says 3. If there are 5 for another node, it will be 5. Why is this relevant? Because from the diagonal matrix, which is related to the topology, and the adjacency matrix, which is definitely the topology, we will be able to introduce the concept of Laplacian. And the Laplacian for this strange structure is looking at the topological properties in a space that is not Euclidean. Still, the Laplacian is a fundamental operator in this space. Then we know that is related to the gradient of the divergence or blah, blah, blah in a continuous space, but this is not a continuous space. So basically what do we do with the Laplacian? We will introduce that. We will look at the information flow associated with a node. So we will somehow embrace the divergence of those edges, and we will look at what is happening inside. That is the concept of that. But anyway, these are the things. Then finally, we have the edge attribute for each edge. We didn't put this, so this one is a vector, so which means that associated to every single edge, you have a vector, which means that the matrix E will be a tensor. If it is not a vector and it is something more complex, you will have a high dimensional tensor, whatever. Okay, so that is the reason why we prefer to put not the matrix, the tensor, but the vector, which is easier to understand. But you have something associated to every single edge. If nothing is there, you have a 0. As simple as that. Okay, so in the following, but later on, I will weaken this assumption. I will say, okay, let's consider undirected graphs so that the matrix, the adjacency matrix, this one, is going to be symmetric. But then in the operators, I will tell you that, okay, so if it is directed, it means that you need to operate in this different way. Okay? Graph shift operator. Okay. A matrix is called the graph shift operator, GSO. If basically says that the generic entry for the matrix is a 0, if that couple I and J does not belong to the entry set. Okay, wow, it seems very strange, but let me go back. So if we look at this matrix, we know this is the adjacency matrix, okay? So we know that we have something different from 0, the black spot, if there is a connection. So if there is an edge, you have a value different from 0. If there is not an edge, you have 0. In that case, if it is the white empty box. That is an example of a graph shift operator, which is formulated in a complemented way because the adjacency matrix is only an instance of this operator. There are more instances of that graph shift operator. So it is just a definition. And so what is said here is that if where anytime there is not a connection, there is zero. If there is a connection, there is something else, which can be zero, but not necessary. Okay. A graph shift operator can be seen, interpreted as some function of the adjacency matrix, because it's very much related to that. So examples. So the Laplacian is a graph shift operator. The Laplacian is D, so the degree matrix, diagonal degree matrix, minus the adjacency matrix. And the random walk matrix, this A tilde, is the inverse of the degree matrix multiplied by the adjacency matrix. There are many others graph shift operators. They are very relevant. Why? Because they will help us to deal with the intrinsic sparsity of our structure in a very neat and compact way. And that is very important. Okay, so if now we have the graph signal capital X, let me recall what it is. X contains all the information associated with the nodes. Okay, the first entry of X is the vector of features associated with that node. You put them all together, and that is capital X. Now, we said that the A tilde, the GSO, is an operator. So if you take the operator and you apply that to another matrix, to the X matrix, what do you get? What you get is X prime, which is the product between those two matrices. Fine. So let me elaborate on this. If we look at what this operator A tilde, again, a random walk or the Laplacian is doing, is that, well, any entry of that vector, so any entry of this one, is basically the weighted sum of the element of this operator multiplied by the vector associated with the node J. So it is a linear combination of what you have. And what you do, you sum over all the nodes, which means that if we are related, this alpha tilde will be different from zero. If we are not related, it will be zero. That is important. So we are just summing up every time we are related. But since we have with the graphs in general sparse entities, so the graph by nature is sparse, which means that if I'm a node, I'm not connected with all of you. So, but only with a subset would be. And it is the very same for every single person in this room. So the structure is very sparse. And this operator is telling us that in reality, this sum goes only in the neighborhood of myself and the node R, which means that if you are not connected with me, the weight tilde AJI will be zero. It is not accounting. So we will have a sum which at the end of the day depends only on the elements that are connected to me, to my neighbors. And this is the notation. So basically we take this sum over the neighbors, which is very intuitive. Okay, now, if I want to apply a filter, let's think of the convolutional neural network. What do? We have the graph, which is the grid. We have a kernel parameterized, which is my sub image, and then we do convolution. We move this small matrix, this kernel over the image, isn't it? But that kernel is characterized by some parameters, which are the elements within the matrix. So they're theta. We need to learn the filters. We need to learn the masks in a convolutional neural network. That is the matrix theta. So it means that starting from what we have here, which is we just apply the graph shift of operator to the graph space. And then what do? You need to do to apply the filter, which is this one. Now, if this filter is a matrix of filters, as it is done here, it means that in a very compact operation, which can be done very easily if you have a multiple processor, if you have a parallel machine, what you're doing, you apply the operator, the filter, immediately for all the kernels to the graph. So the side effect of this notation is that what you do is you look at one hop neighborhood. This is what is doing here. And with respect to that one hop neighborhood, I apply a set of filters. So I look at the three of us, I apply the first kernel. And then I take the three of us, another kernel. And then another kernel, another kernel. Those kernels are in the matrix capital theta that we need to learn. And then what do we do with convolution? We have those kernels, we move them around, but they're always the same. But what is changing? The pixel, central pixel, which will be U, the node. So we move this kernel around and we do convolution over the original matrix, which means over the graph. And this is represented by this very compact notation. What does it mean? Well, if you look at what is going on, it is saying that the output of the convolution is this H, is a vector for myself, and it will be associated with the first kernel applied to my neighbor, the second kernel applied to my neighbors, the third kernel applied to my neighbors. And then I change I over the number of nodes, it will become U, and so on, and I have the convoluted structure. Yeah, we have a local filters, I and my neighbors, one hop neighbors only. The filters are capital theta, and when I move to U, they will be still capital theta. It is exactly what is happening in a convolutional neural network, where you learn the first kernel and you do convolution. Then you get a feature map. Another kernel, you do convolution of the image, the second feature map. And then the third, and so on. You see, all these, the output of the convolution is exactly within this capital H matrix. We were looking at one hop. And you might say, yes, but I understand that we want to do convolution with my closest friends at first. But what about if we take a two hops convolution too? Maybe that the information will be less, but it is something that we cannot discard. So we need to find a way to do convolution at the second hop, third hop, getting far from where I am. Okay? Before doing that, if we are able to do convolution over all the kernels, and you guess, you bet, we will learn these parameters end to end when we solve our task. Like in a convolutional neural network, deep convolutional neural network, you have all the parameters associated with the kernels, the masks, the filters, if you wish, and you learn them end to end with your problem. So we will learn those parameters. And if you do convolution, that is a linear operator, you're happy. But in deep learning, you want to do convolution, and then you want to change the manifold. You want to apply a nonlinear function. And then again, maybe convolution, and then nonlinear function, you know, a set of a convolution with the nonlinear output. So what we generally do, we apply also this sigma function, which is a nonlinear function. It can be a ReLU, P-ReLU, it depends. That is a hyperparameter. And then at the end, I will give you one of the next slides, I don't know when, an architecture which is always working very well. So if you start with that architecture and you don't get any improvement, it means that probably using a graph is not what you're supposed to do. You were believing that there was structure in there, but if you don't get any improvement in accuracy with respect to your task, maybe that you don't need to follow the path. Like Jung was saying back in time, if you have an ARCS model and you try with 2 and 2, if you don't get anything from there, give it up. Okay. But anyway. This operation is differentiable. So if we look at this operation, it's differentiable with respect to the parameters, which means that if we want to learn through gradient descent, we can. Okay, so, but that is enough in a way if we want to design some graph neural networks, as I was telling you before. So in a graph neural network, which was the evolution of the convolutional neural network, we were doing, what were we doing? Convolution, nonlinear, and then you shrink pooling. But you might decide not to shrink, you don't need maybe pooling, you know? You do convolution, nonlinear, deep. And at the end, you make a decision. Pooling is necessarily, why? Because otherwise, if you start from a picture and you do a kernel, you generate the output, the Fisher map, that has more or less the same dimension of the input matrix. So if it is 1 gigabyte, your picture, you will get around 1 gigabyte. That are just the borders of the convolution. And if you apply another filter, you have another gigabyte. You apply another one, another gigabyte. Instead of shrinking information, you amplify. So pooling is necessarily only to bring you back to reality. Otherwise, it is not necessary. And for some people, there is also a school of thought saying that you should not do pooling. Why? Because it is a low-pass filter most of the times. And so if it is a low-pass filter, you are always cutting down the frequencies, a high frequencies component, and then you should find a way to propagate those, that type of information, high frequency information, to the next layers. And that is why you have those jump connections that bring you some information to the next layers. Anyway, so we can design graph neural networks. And now we might ask, okay, if I have a convolution layer and I apply another convolution layer. So first layer, second layer. No, I don't want to consider non-linearity in there. So I get rid of the non-linearity. I have the first convolution layer, and then we introduce a second convolution layer. What am I doing? What is happening? And we can address and solve this problem by looking at the graph shift of. So if So this is the first convolutional layer, linear. We apply these kernel matrices, these theta 1, and you get the convoluted image masks, capital H1. Then what you do, you take this H tilde 1 and you iterate, you apply the graph shift operator, and then you have a new filters because that is the second layer. So that was the first layer. Now theta 2 is the second layer. And that's it, basically. So, which means that if you rearrange, you get this stuff, and you see that that is very important. What you do is like having A tilde square. So you take the graph shift operator to the power. When you go through the understanding of what this implies, so when you look at this polynomial way of applying the graph shift operator, you will be surprised, or maybe not, to see that what is happening is that you are dealing only with the nodes that stay at a distance from you of order 2. So the graph shift operator, power k, means that you want to treat the information that is k steps from you. And those, if you look at this polynomial behavior, allows you to think that, well, why not then consider polynomial filters? So I say that my new value, the convoluted value, will depend on me, and then I want to process only my neighbors with a capital matrix theta 1, plus some other contribution which depends only on those friends which are not related to me, but they are indirectly related. Hop number 2. So plus A tilde square, and then they will have their own filters. Would you like to go back to K, L, whatever, A tilde power K or L, and then the other things. So in a way, you say that the information I'm getting now depends on me, on my 1 hop neighbors, 2 hop neighbors with other filters, 3 hop, and then you decide when to stop. Okay? It's very neat, beautiful. Why? Because those are just tensor products. And they are very effective. So if you want to compute only something that is a distance k from you, you apply the GSO power k. If you do this operation and you go far from you, you will see that the matrix that you get, which is, I don't know, A tilde power 5, will be dense, very dense. So everything is connected to everything. The number of hops depends on the problem, and that is a hyperparameter. But on the average, you go to 3, 4, that is what. Okay? Okay, so that was the comment I was doing to hop neighbors and so on. So we found a very nice way to deal with something that is far from us and to aggregate the contribution coming from those guys in a very nice way, easily to be computed. Otherwise, I think of computer science. If you have a graph, it means that you have a dynamic allocation of the memory, you have a list, but there is a double list, which means that you need to enter into one, and then sequentially you go through that, you find the element, you do multiplication, you roll back. I mean, if you have a program, the list and all those items, it is pretty tricky. In this way, it is just a tensor. Okay, so this is what we were looking at. So if you want to consider the contribution coming from step K, then you just simply take the GSO, the graph shift operator power K, you apply that to your signal, what you have, and then it will have its own filters. Or if you don't want to do that, you do that sequential. So, which means you apply the first filter and then another layer, you do the second filter, and then another layer, the third filter, and the effect is going to be the same. So that implies that we can put everything together in only one convolution layer. Then, if you want to go deeper in the architecture, you can do it. But only if you're introducing some nonlinearity between those layers. Otherwise, the effect is that I'm just going to consider something that is far from. Nonlinearities, otherwise, I mean, it's linear. I'm just going getting further from me. One, first line, second line, third. But maybe that up there, they don't even care what I'm saying. Sorry, no, I didn't want to say that. But, which means that the contribution you give to me is negligible. So I won't be interested in that, you see? Okay. So, some examples of the convolutional filters and layers that we use in the literature. So we said that the GSO, the graph shift operator, we said that it is very much related to the adjacency matrix. It is helping us to go far if you take the power of that. In the literature, there are different propositions. So again, D is the degree matrix. The cap A is the adjacency matrix. IN or 1n is the diagonal matrix with only ones and zero out from the diagonal. So why are they used? In order to keep under control the generation of numerical errors, things like that. Because then sometimes you need to compute eigenvalues, eigenvectors, and you will see that. Anyway, okay, so there are different ways to do that. And okay, but to sum up, graph convolution based on graph shift operators are very powerful to learn graph filters, and they depend only on the graph topology though. Because if we go back here, and we look at what we have here, there is only information related to the degree of my nodes, or A, which is the adjacency matrix, so only the topology. So, and if we go back once more, what we see here is that we have, we apply topological information, which is this one, to information associated with the nodes, and then you have the filters. So in this way of thinking, we are only processing information associated to nodes. What about edges? If we have edges, and the edges have information, apart from the topology, and we want to process that information too, it is not enough to use this structure. So this one is perfect if you have a graph where all the information is associated with the nodes. If you have a sensor network and you know that I'm related to you, why? Because if we have sensors of the same nature in this room, they will be related by definition because of the physics. So I might decide to build a graph by saying, this temperature sensor is connected with that temperature sensor. So only topology, you see? We don't need to say, how much are you related? I don't want to use Pearson. I don't want to use Granger causality. I don't care. I just want to say they are related. So only topology and the information they are measuring is enough to solve the problem. But if on the top of that, you look at the edge and there is information associated with the edge, you need to process things in a different way, to do a further extension. Okay? And that further extension is called message passing. The idea is very simple. So, apart from the okay, so they depend on the topology, they are shared, they are localized. So yeah, I mean, and if we have edge attributes, it means that we need to use the same structure, but we need to process the information coming from the edges. And so not only topology, blah, blah, blah. Okay, so it's message passing. Message passing is just a name for something that when you will say, is that is? Of course it is that. It's very simple. Okay, so now we have the graph, we have the sensors. I will use the sensors so that is easier somehow to understand, okay? So each node has sensors. So we have this information, we have the topology, we can process that. But now I'm telling you that on the top of that, we have this vector of information associated with the edges. I'm exchanging a message to Marius. It is text. Through a bot, I take the text, I extract only some keywords. Okay? I build a vector. That vector goes with the edge. That is an example. Okay? And then if I'm going to vote red, you are going to vote red, red, yellow, red, yellow, yellow. And for the others, Marius too, we don't know. But by processing that feature associated with the edges, I will be able to predict what Marius is going to vote. That is the point. And I will do a demo at the end, which is not related to the vote, to the polls, but keep in mind that was used in the US at Trump time. So during the Trump elections to try to understand how the people were voting. But if we want to do this, we need to extend the previous architecture, and we need to take into account edges. So we have this graph. Now we have vectors associated with the edges. Again, if there is a 0, means either that you don't have the sensor, or that information is not existing, or whatever. The idea of a message passing is that if we are connected, we want to share information. And the information that we exchange depends on me, Marius, I'm sorry, on you, and on the entity, the features associated with the edge between Marius and me. That is the idea. Very trivial. So basically, I'm here. I have a vision of the planet. I want to change my vision, my state. And they say that I will change my state based on where my previous vision, on what Marius believes, which is amplified by what is in the edge, and that will be his contribution. But then I'm also connected, I don't know, to Stelios, Christos, Thomas, and so on, Mihalis, whoever. And each of them will provide a different view of me. So I will say, give me your interpretation. And you say, well, I mean, I'm here. I believe this. I look at my features. This is what I believe. And then I build a message, which is what you believe, who you are, there are the features associated with the edges. So you mix everything together and you provide a piece of information. I collect that information, I add it with all the arrows, and I decide to change myself. As you can guess, I might decide to weight in a different way, Marius or Stelios or Christoph, whoever, according to some, okay, so we will see some attention mechanism. Why? Because now it is more relevant you than you. But next time, it may be that Christos is more relevant than Stelios. So you have an attention mechanism. You will change the way how you deal with this thing. That is what transformers are doing as well. Think of large language models. So you have all these attention mechanisms that is saying, okay, this token, this tokenized. You put everything together, you make a decision. And then you change something, okay, everything will change. And we will learn all the parameters end to end. So the relevance of the connection, the weights, the masks, the filters, whatever. But so the idea, as I was saying, you see. So I'm here, I'm in the center. What I want to do is to get messages. I build messages. I take all the information associated with the nodes and I do an embedding. So I do a nonlinear transformation of my view of the time. You have a vector, you apply nonlinear mapping, multi-layer perceptron generally. You do a shift, you change the things, and you say, this is my representation of what I have. And each of us is doing the same. So each of us is applying the very same nonlinear function, which need to be learned. So it is a nonlinear transformation of me. So you start from another task. You start from my information, from my vector of information, and you apply something, you reshuffle everything in a nonlinear way to generate the concept of state, if you wish. It is a nonlinear state. I'm using this word not in dynamic terms, but just to say that you reshuffle, you change something, and you say that this is me. And then each of us is doing the same. Finally, each of the neighbors send a message to me. This message is composed of the reshuffling of your information, and it depends also on the information associated with the edge. So they build this message, they pass it to me, and then finally I collect all the information coming to me, and I change myself. And then you do this for each of you. So you see, it is an extension of the concept of convolution, where I'm doing some pre-processing of what you have in a nonlinear. But we will see that. Okay, so the general scheme is very, very simple. Let's look at it. So you say that each of us is generating a message through a nonlinear function, which is this phi, correct? This phi. This phi depends on me, Marius, and the information between the two of us associated with the edge. We take these three pieces of information, we mix them in a nonlinear way, and that is the net contribution, the message. And then what do you do? Well, if I'm the node I need to aggregate with respect to my neighbors. So I do this with Marius, one message, with Christos, another message, Stelios, another one, whoever. And then I have all these contributions and I aggregate them. And that is the aggregation function. Then I have my own view, personal view, which is the xy. So this was me before. So I mix all together in a nonlinear way, gamma, my previous information with all the contributions given from my one-hop neighbors, 2 hop neighbors, k hop neighbors. Okay? And that is my new view of the planet. We apply these nonlinear functions to all of you. So the convolution now goes around, and we will re-update the all-over view of the graph, which is not only at the single node, but for everyone. And then you iterate this. Okay, so the message pass depends on the edge attribute. Generally, this aggregation is a permutation invariant aggregation function, sum, mean, max. And gamma is an update function. Just to understand, the phi and the gamma, most of times, are multi-layer perceptrons. Because we don't know which gamma we should consider. We don't know which phi we should consider. So we say that those are parameterized. And then we will learn the gammas, the phis, end to end with my problem, with my task. Okay? So at the end, everything will be a crunching machine where you need to learn the parameters of everything. And by doing that, we will weight in the proper way the contribution of each of them. Those functions will move around. So if this is what we do for me, which is I'm node I, then the very same structure with the same gamma and the same phi will apply to each of you. And that is the concept of convolution in convolution neural network. You have one kernel, one mask, which goes around over the pixels. Now, that kernel, that mask, is this function that goes around in a nonlinear way. So as I said, phis and gamma are usually parametric, they're multi-layer perception. They can be deep, they can be whatever. Okay. So the message passing equation is the most general one. It's very intuitive. I mean, I'm just saying that my view depends on yours, which is a nonlinear. It depends on mine, on yours, through the strength of the connection, if you wish. And then we weight that in some nonlinear way. And then I make a decision on myself. I update myself in a synchronous way. And then I apply to every single of you, and I have we have a new vision of the planet all together. Okay, so convolution is a sub-case of this, which means that if you remember, I was saying that the convolution layer, the graph convolution layer was this convolution, in this case is one hop convolution through the a tilde, and then you have a nonlinear function. Clearly, this one, which is again one convolution layer in the graph neural network, can be cast in this same notation, where the application is the sum, the time is the sigma, and blah blah blah. Okay, then you have isotropic, not isotropic. That it depends. So if I update my view only by looking at your vision without using edges, there is a name, and it is a case. Not even worth to spend time on this. But what is relevant here is the graph attention network. Why? Because now we put attention. I want to say that the message that you send to me is more relevant than the message that you sent now. Tomorrow, it might be different. Okay, like in transform. So you have a text. Now I'm saying that in order which it will be the next word. I don't know why, but I take from this token and that token. And all the others I ignore them. And then I will change myself in a nonlinear way in order to make the next forecast for the board. exactly the same. I'm saying that given the fact that I'm here at this time instant, I will consider more your information than yours and yours. Why? Because at the end, there is the attention mechanism. Maybe that you are familiar with the attention, for sure. You heard about the attention mechanism. So let's see how it operates. So at first, you have a filter. So the attention mechanism comes with some parameters that are associated with the features, the edges. So I want to give a different relevance to them, a different weight. But this weight changes over time. It's not the same. Okay. So at first we do the convolution, one hop convolution, you get X prime. Then you need to compute the attention score in this way. So we apply the convolution, I and Professor Policarpo, we apply the convolution. Then he says to me his convoluted value, and I just oppose that view with my view convoluted, which is what we are doing here. And then we have a longer vector, and we apply a nonlinear parameter, which is this theta 2, and then we apply a nonlinear function, a sigmoidal function. And what you get is a scalar. When you have this scalar, you normalize this according to the attention mechanism, which means you take the exponential of that one, and then you normalize that with respect to all the neighbors. What you get is the attention. And you use that value, that scalar value, to weight the message, the contribution coming from it. And then my view depends on how this attention mechanism is filtering. It is like a game. It is an adaptive game on the message, on the piece of information you send. And then we aggregate everything, and I make my own decision. And next time, new data, new features, and so on, I might change. I might say that now I disagree with Marius. So I will weight his contribution much less, depending on the input. Clear? These are the graph attention networks. Very powerful, very bad. Okay? Well, you see that there are many, many things, different architectures, which depend on the problem and on what you want to do. Do we believe that we are all the same? All pigs are the same. Okay, you don't need attention, but some pigs are more pigs relevant than the others in animal farm. So if some pigs are more relevant than the others, more important, then that is the attention, you see? And then you change the architecture. It depends on your prior, on the deductive bias you have about it. Okay, so what do we do? Okay, this one is the edge condition convolution. Many varieties. You say, okay, let me start with the features we have associated with the edges. Vector. I don't like that. I want to do an embedding of them in some nonlinear space. So you take a vector, you apply a mapping, you end up with another vector. Why? Because you want to give a lot of value to those features. And you don't believe that if they come as a vector and you treat them as a vector in the proper Euclidean space, it is correct. So you do a nonlinear mapping, and then you do whatever is needed. So if that is what you want to do, the architectures are edge condition, and basically you take the features associated with the edges and you apply a nonlinear function rho, which again is multi-layer perceptron that is shuffling everything and generating a new view of yourself. And then you update your state based on, you say, okay, the linear convolution as before, and then you weight the edges in the propagation. So yeah, there are many linear convolutions. There are so many that if you look at the literature, each of those methods recommend a message passing for your program. All of them are coherent, depending on the priors you have. So if you know that this is true, then you should use this one. If you have a locality in space, you should use this one. If you don't believe that everybody is equal, you don't want to give the same confidence attention. If you have edges, you use another one. If you don't have edges, information associated with the edges, then you can use only the GSO, you know, different variants. So it is a mess, but what you can do, you can put all those methods all together. And you learn what is needed based on your program. Which means that again, end to end, which means I have my graph. At the end of the day, I want to say that Christos is going to vote red. Inside, I will have all the parameters, the filters that need to be learned. All the multi-layer perceptron doing these embeddings. And then, having that, I do the convolution. And they will say, okay, you told me that you were voting blue, fine. You were training set. But if you didn't tell me how you were voting, I tell you that you will be blue, red, 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 blue, blue, blue. Okay? That is what we are going to do. So, and we will learn everything end to end. Getting rid of all this stuff. Okay? So, a good recipe. I was saying this before. So if I have my program and I want to try to do a graph neural network to try to solve my task, whatever the task is, what am I supposed to do? Which architecture should I consider? So a good rule of thumb is to consider this architecture. If you get an improvement, it is worth to go deeper and try different solutions. If you don't get an improvement, but first you should ask why that is the case. And if you are convinced, then you give up. Okay? So basically what you do, you take your data, node features, edge features, and to each of them you apply a two-layer, multi-layer percent. Which means that that's me, this is my vector of features. I apply a multi-layer percent, two layers, a deep one. And I will use the very same architecture for every single item of it. If now I'm considering the edge, I will learn another multi-layer perceptron operating at the edge level, but it will be shared. It will be the same after learning. Why? Because that is the principle of having convolution. So we all do together a map and embed it into some nonlinear space. And this is the reason why we have this. And then we apply message passing. And nonlinear, clearly, it can be between 4 and 6 layers, which means convolution, blah, 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 nonlinearity, convolution, blah, 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 nonlinearity, convolution, nonlinearity, convolution, nonlinearity. And then finally, here, you will have, so at the end of this process, so you start with a graph, you apply a nonlinear function to the information in the graph, but still you have a graph. You do message passing, you have again a graph. Another message passing, you have a graph. which is updating. And then a graph, and then you stop, which is what you do here. And now it depends on your problem. And if you want something at the graph level, you unroll the graph and you get one value. The power consumption in electrical power consumption in Nicosia tomorrow morning at 9 a.m. Okay, one scale. Or you might say, yeah, having everything together, should I say that the image contains a bottle, a mouse, a box, whatever, classification? Or I might say, no. When I look at this graph and I apply this two-layer perception to every single item, then I look at the output. And the output might be, if it is at the edge, it's telling me whether we are related. If it is at the node, which will be your forecast tomorrow, if you are producing, if you have, I don't know, a wind farm, or any other value, or what you're going to vote. That is the other possibility, you see? And then you train end-to-end this architecture, which is indeed deep. It is a processing the graph up to the point where the graph can be kept or degenerates depending on the task you have. Is that clear? That is what we do. If you don't succeed, if you don't see any margin of improvement after having done this in a proper way, it means that, as I said, first you should wonder why. Well, maybe that your problem was so easy that what you were doing was enough. It was not worth to take into account all the dependencies, topologies, and so on. But believe in me that if the dependency is there and you don't get an improvement, something is wrong in the way you're treating the data. Okay? So, message passing layers. So, you should consider this message passing, which means that linear convolution, so something very simple. Batch NOR, you are normalizing the contribution coming from the neighbors, like a normalization. So you center yourself with respect to the expected behavior. You normalize with respect to the standard deviation of the spread, these type of things. That is the batch NOR. Then you apply the ReLU, so rectified linear unit, which is parameterized P, which means that you have an extra parameter that you need to learn. And that is the structure. Then the aggregation in the message passing is the sum. And for the update, you make a juxtaposition. So what does it mean? That my new state depends on the previous state, but is not substituting the previous state. So I will keep my previous state, which is this vector. Now I have a new state, which is this other vector. I put them together, one by the other. So my state is increasing. Why? Because we don't want the low-pass filters to destroy the information content. So you do this 4 times, which means that at the end, at this layer, you will have a very long state, which is coming with all the processing at the different levels. And you consider that in order to make a defined solution. It is, as I said, a rule of thumb. But you should start with this one, and then I will tell you that there are libraries and so on. Then if you want to play, clearly you play different items. But if you don't get anything there, something is wrong. Okay, so So how do we use this? That is what I was saying before. You start with a graph. You have features associated with the nodes. In a social network, these entities are people. What is the features in the original graph is the text that you write, not all the text, the messages, but we extract some keywords. So you do a hot encoding. So if you talk about guns, explosives, and so on, maybe you are a suspicious person. Okay, so this it depends on what you are looking at. So if you have this and you are interested in updating your views, it means that you start with something and you update over time your perception until when we look at the new picture of the graph, the new picture is providing what I'm looking at. Is again the forecast of how much power you will need tomorrow at 10 o'clock for your home, your home, your home, your home, your home. Okay, one picture for tomorrow. And that is what you have here. Or in the second one, for molecules, for instance, you start with some chemical compound, which is this one. You apply a nonlinear multilayer perceptron to every single node, which means you are starting with the oxygen. And then you process that and it is becoming something. And then all the message passing are taking into account all the bonds, the chemical bonds that you have at different hops, which is coming from this layer of a message passing. Because if you remember, with the graph shift operator, if you put one and then another one is and then another one is like going back, coming and considering something which is far from. So clearly it has to be linear, but in this case it's not linear. So this one is basically looking at one hop. This one is looking at 2 hops, 3 hops, 4 hops. But then the update is taking all these states. So I take my vision at 1 hop, my vision at 2 hops, at the 3 hops, at the 4 hops, and finally I make the final decision. And which is this one. Sorry. So in this case, at the end, you get an updated graph, and then you converge to a number. In this case, the task is at the graph level. You look at the chemical compound, and you look for the solubility in water or in alcohol of that compound. And it is a number, okay? So it is one number, but in doing that, you need to process all what you have. And think of the chemical bonds, okay? If the oxygen is 2 or it is 4, blah, blah, blah. So yeah, that is an example. So I'm saying graph convolutions act as low-pass filters. So pay attention to that. And in order to get rid of this, what do? We try to keep all the convolutions and we stack them one after the other. Otherwise, you know, if you have a number, you apply logarithm, logarithm of a logarithm of a logarithm, everything will be linear at the end of the day. Okay, so you trivialize. So what you get is something which is silly, not relevant. But if you put a juxtaposition, you increase your state, and then at the end you make the decision. Okay. Pooling of graphs. What do you think? Should we stop here today? Or maybe I can, 5 minutes, I give you the idea of the pooling, and then we stop. And tomorrow we start with, again, pooling. Pooling is very interesting because you start from a huge graph, and you start grouping, clustering together items in order to get something that hopefully does contain the same information content, but shrinks. It comes with a cost, but has also many options, and so it is interesting to see. So, sorry, let's try to understand pooling. We saw that already, but let's have a look at that. So, graph neural network, as I said, pooling shrinks. Do we need a pooling? Some people believe that it is not needed. It is harmful. Why? Because it is cutting, removing information. But if you apply convolution and the locality principle in time and space was there, it does make sense to do pooling. Why? Because if this one is gray, this pixel, this one will be gray too. So I do convolution and then I shrink. You see, am I losing information? No. Am I assuming that there is noise in the picture? Indeed. Which maybe depends on the point, maybe not. Okay, so you can do all the estimating you want. So it does make sense. So it is not a harm. But in some cases, if you have the input is changing dramatically and you apply pooling, you do disasters. So in many cases, as in the previous case, let me go back because I think it is important. In this architecture, I was proposing as a trial, there is no pooling. Don't use pooling. Try that one. Do you get an improvement in your problem? Yes, you explore pooling, whatever. You don't get an improvement, okay, give up. Or try to understand why. But if it does make sense and pooling is possible, you deal with the computational complexity because you shrink everything. It is makes more sense, and you have something that is also computationally doable. Okay, so pooling of graphs. Let's start again with the convolution neural network. What is pooling doing? Well, you take a pixel, which is this one. You process the pixel, and then pooling is doing aggregation, which means that if you start and you look at this pixel will be lost in this 2 by 2 square. That is an example of choice of the pooling size, you know? So you are losing that piece of information processed within a larger square. And when you look at your picture, it is a shrinking. So you have it is like building some abstraction layer. Instead of looking at the detail, you abstract it and you look at the coarser resolution. And then when you look at that pixel, if you apply again pooling, it is becoming lost in the middle of the other ones. Fine, you're abstracting. And then abstracting again, it is what convolutional neural networks are doing. And then you make a decision about the content of your picture, maybe 1024 classes, okay? AlexNet or whatever. Now, if we have a graph, we should try to keep the same concept. So pooling should be able somehow to look at the coarser level, to abstract, to get rid from the detail. You do processing, you do convolution, which is helping, and then you get far from the pixel and you look at that. And then you do something, and then you look again further away from that. You want to lose details if you want to abstract. So we start with this node. This is an example. It is a pixel. And, and then what you do is a one-hop convolution, if you want. Or, which is the same, we make a decision out of this pixel, 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 pixel. So we group these pixels, these nodes, all together in a single node. And then if we apply again pooling, then you color, I hope that you can see the pinkish value up there, you color, so you abstract the level. and then again, okay? So, okay, let's do it. Let's do this. So how can we aggregate cooling? This is very trivial, but then you say, well, I already know, Mario. You say, yeah, we have been doing with iSense or this grouping of the entities, blah, 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 but you cannot apply these techniques. Then we will see tomorrow that we will learn how to do clustering. But conceptually, if you want to shrink, to aggregate a graph, well, you take the nodes. These nodes, 1, 2, 3, they are similar in terms of attributes. They go into one node. This one. You shrink them. Maybe you take the average of do something, some processing in order to go and degenerate to this node. And this one, well, this one is different. So you keep, or you aggregate clicks. What is a click in a graph? So you have, it is a subset of the graph where each node is connected to any other. So if we are all together so strictly related, we can collapse in a single meta entity. That is the idea. It is very common to find triangular clicks like this one. So this one is a click and degenerates in this node. This one again is another click and degenerates in this node. Okay? Or you decide to keep only some colors. You're only interested in some features, so you say, yeah, I mean, this is my graph, but I like only the blue and the red points. And then you discover for the others. That is another thing. Okay? 3 main questions, and then we stop. How to identify groups of related nodes? So I want to say 1, 2, 3, and that's it. Why that's it? And if we are able to say that we should stay together in a meta entity, what about the new attributes of the node? Well, it will be a mix of what we believe, that is fine, but how? And if we group together, so you group together, you group together, you group together, you group together, you update your state altogether, and who is connected with whom? Are you going to be connected there? Or you say, no, I don't want to be connected. I want to be connected with the other one. It is not up to you, it depends on the topology. You see? So the third question we need to answer is how to connect these entities. And this is what we will see tomorrow. I think we can stop here. Okay? If you have questions, I'm happy to answer them. So tomorrow we'll finish this part, so I can anticipate some spoiling. So we will finish this part. There is a demo. So we will see the real value of using these graph convolution neural networks on a real application. So we will see when we get value. And then we say, okay, we like space, but that is not enough. We like time too. We like dynamic processes. So again, convolution, time and space. And then should I do time and space, space and time all together, blah, 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 and so on. This is what we're going to see. Okay?
I have many, but
oh, come on. That is not going to come maybe for your question. Why are you saying that? Oh, someone has to be there.
Maybe you will talk about some of I'm asking for tomorrow. So
Maybe not, yeah.
So the first question is, will be the time-space separation there? So I'm a bit curious about learning about that, because the way I understood what you said is that in a way the graph is fake. Okay? And then you learn, and it takes time to learn. But this is not what happens in many networks. The graph is continuously changing. And that mixes up with the learning of the parameters, and so on. So is there a need of a time-space separation or not?
Okay, I don't know if I got it, but let me try to answer. So, if you have a sensor net, you have the structure of your graph. The topology can change. Why? Because if a sensor is running out of energy, it will be off. And then it may be back. But it doesn't imply that your task is not going to be successful. No, so this is the first point. So things can change when what we do here, we just needed to dimension the maximum size of your structure. But the graph that you are receiving from your process generating the data is changing in topology every time, or not. That is the first point. If you assume the process to be stationary, okay, that is the assumption. So you might get something. I have now 10 nodes. This is the topology, like in the enzymes. And 1 hour from now, I get something different. There are only 2 nodes. And I do by processing. If that is the case during the training time, during the training procedure, you will experience of these graphs coming and changing in topology and attributes and so on. So during the end-to-end learning, where you learn all the multi-layer perceptron doing aggregation, message passing, and so on, under the stationarity assumption, what you build is correct. Now, if now you introduce time, and the time can be intended in 2 ways. At first, you relax the idea assumption by saying they are time dependent. So what you have is a stochastic process where each random variable will have its own PDF, but is generating a graph with its own topology. Okay, like we do in all system identification, but now they are graphs. And but if the process is time invariant, we can learn all the transformations and whatever is needed in order to build, I don't know, 1 step ahead, a predictor or whatever. That is the first part. If it is a time variant, then what you have to do is either to look at the sequence of graphs coming to you and detect the change in time variance. So it is now becoming a time variant process. Clearly, it is dynamic. Okay, but it is now becoming time variant. And there are tools, there are statistical tests. This is called learning in non-stationary environments that are telling you, hey, something is happening. Like QSUM test, okay? Going back to all the good days of system identification, okay? Something similar. It is based on QSUM, blah, 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 graphs, whatever. Okay, sound statistics and so on. So that is one possibility. Or the other possibility, if you have a time variant process, you apply a graph Kalman filter, which means that you need to be in the Kalman setting. And you might say, yeah, but I know maybe the distribution for the input state for the graph, for the input of your graph, the output, but what about the state? I don't know the states. So how should they look like? Now, there are methods where you learn the distribution of the graph state. Again, end to end. When you do this, then you apply a Kalman filters, if you can do that, which means that you have a new value, you had a previous estimate, you look at the innovation content, and you update. again, you are in a framework where the topology can change. So yes, you can learn the distribution of some latent state, which is a graph. Yes, you can. There are many techniques. It's called the graph learning. So you don't know the graph, you want to learn. And well, the second one is associated with Kalman. Okay, so you keep track to the process which is drifting away according to stationary time variance of the process, not the dynamics in shifting away. Sure.
So you talked before about the emotional prior information and how you can incorporate these into the care that, for example, that you plan. So could you provide some guidance with respect to how you can do that? I mean, how you can relate, for example, careness to information that you have about the system?
Okay, so to me, the prior information, the first one is what you're looking at is a stationary time invariant. If it is not, which is the drift, how fast it is drifting away. Because otherwise you are following something, you're building something which does not make any sense. And instead of considering a multi-layer perceptron, you need to start with recurrent neural networks because everything is drifting away, blah, blah, blah. But if it is stationary, or we will see tomorrow, time invariant, what now you have, the other prior you have is related to the graph nature, which is mostly associated with the topology, which means that if you have a sensor network, just to understand, how can I build the topology? You can use some Pearson coefficient trivial or Granger causality. So this signal, my signal, with your signal together are able to predict what you're going to do in the future in a linear way with respect to a finite time horizon. And then you build the topology, okay? Another prior is that when you look at the topology might change over time. And if you tell me that the topology is changing over time with respect to some probability density function, or it is changing in a smooth way, or there is a distribution, because you know it is drifting away, or it is changing, and you don't know the distribution, and you want to learn the distribution, which is parameterized, you can do that. And now that is part of the prior. You change the major assumption always is a stationarity and time invariance. For all the others, if those two hold, you're able to do something. Either you learn the graph, you build your priors, you know. If you need to do that, I'm thinking of a sensor network because of your programs, okay? Yeah. In forecasting traffic jam and so on, graphs are widely used. We use them by ourselves. And what you get are superior performance compared to all the other methods, which makes sense.
Tomorrow we start at 9:30.
Okay.